Welcome to everyone to this virtual, a bit strange conference. My name is Elias Josephsen from Norway. I'm the creator of Rustler, and I currently work as an architectural engineer at Dockyard. And most importantly for this talk, I'm also a Lumen core team member. This presentation, Lumen and Eir, focuses mainly on the Lumen compiler. So note that this presentation starts off with a high-level overview, and then it dives down a bit more into the more nitty-gritty of the compiler. So regardless if you're familiar with compilers from before, or if you're pretty new to them, you should hopefully get something interesting out of this. So let's get started. We will start off with the Lumen part, and I'll get to EIR a bit later and explain what that is. So Lumen, it's a greenfield compiler and runtime for Beam languages, which was first started at Dockyard back in late 2018. And it was first unveiled publicly at ElixirConf EU 2019. We have, it's a compiler, so we're not an interpreter or like a VM. So we compile directly to the target code where the Elixir application runs. So right now we have two main targets. We have the WebAssembly target and we have the native target. And as you can imagine, there's for each target, there's a wide range of different possible use cases. You have the primary target, WebAssembly, which was mainly envisioned to write browser apps, but there's also a couple of interesting possibilities, like CDNs like Fastly have started offering the ability to run WebAssembly on the edge. So that opens some really interesting possibilities if you can distribute out your Elixir application onto the Fastly CDN and run stuff on the edge there. Native is really interesting too. It's not a primary right now, but we use it for running tests and stuff like that. So it should be really a really good target as well. So possibilities for this is server deployments. You can imagine where you would run a traditional Elixir deployment with the added advantage of having, say, just a single static binary that you can just start without much trouble, which could really be nice for ease of deployment. And for some more interesting stuff, you could imagine running native GUI applications. This probably makes you think of Scenic, which, I mean, being able to run GUI applications as a single binary makes it really easy to distribute them out to people, and that should hopefully be nice. And a possibility is also big embedded in the sense that it's more like what nerves would run on, like a relatively powerful machine that can run like Linux or an OS. But then there's also the interesting target, which is not, or a really interesting target, which is not focused on or even supported right now. But you can imagine being able to run Elixir on small to medium or medium to large microcontrollers without an OS. So like Elixir on your toaster. I don't know if you would want that, but hey, IoT, I guess. So yeah, in order to support these different targets, we have a wide range of requirements that we need to support. Just as some examples, we have, if you want to run something in a browser, then code size is really, really important, right? You don't want you want the code size of your application to be ideally smaller than what you would get when writing for a regular JavaScript framework. And startup time is also really, really important. If your application takes 10 seconds to start up, the user is probably not going to have a good experience. However, performance, yeah, it's important. You need to click in a button and get a response pretty quick, but you're probably not going to be running machine learning or big number crunching in the browser. You might, but that's probably not the most important part of the browser target. Contrast this to something like running on a server, where startup time and code size is really, really not that important, but performance starts getting like really, really important. So you want your application to run quickly to serve as many users as possible. So clearly we need a really scalable solution here for our compiler. But we cannot perform magic, so we need to make some trade-offs. And the two main ones we're making are we don't support hot code reloading at all. So once you compile your application, it's gonna run that code forever. And when you want to change out the code, you need to restart it. And you can imagine for the WebAssembly target running in the browser, this is probably not a very big deal because the user is going to reload your app soon, regardless. On servers, if you want to do hot code reloading, you use the beam. We are also AOT compiled. We're not interpreted. And we mean this in a different sense than, I mean, Elixir and Erlang, they're compiled too, but they run on a VM, an interpreter that interprets bytecode. So we compile directly to machine code of the target. So to look at this a bit more, eliminating hot code reloading has some big advantages for us. We get some really interesting stuff from it. And the main things we get is that we know all of the modules that exist in your application at compile time, and we know that code can change out under our feet. So that really enables more aggressive cross-module optimizations. So we can do stuff like inlining functions across and hopefully get better performance in that way. And perhaps more interesting for the browser target is that since we know all of the code that your application encompasses, we can look and see if we know that a function is never called by anything. If we can prove that, then we can just remove it and not ship it in the binary. And that applies to whole modules as well. So if you pull in the dependency but don't use it, then that shouldn't blow up your code size, final code size. There's also, say if we have a function that we know only returns an integer, when we know that the code can change in the middle of running the application, then we can utilize that information like in other modules. We can both eliminate other code paths, so make the code smaller, and we can specialize the code for that specific type to make it more performant. And there's also like way more we can do with that, really interesting possibilities. And we are compiled like directly. So this should hopefully improve startup time in the sense that we don't need to run any start scripts or anything like that. And the startup procedure can be static and fully optimized by the compiler. And specifically for the browser target, since we already have a virtual machine or a runtime that runs our WebAssembly, we don't want to have another one on top of that, right? So the code gets compiled directly to WebAssembly and it runs directly on the WebAssembly VM. And then that, like if your WebAssembly engine has a JIT compiler, then that can take care of doing optimizations there. We don't need two levels of that. So like what you should get from this is that the compiler is really, really important for us. Now I'll get to the specifics of what we do in the compiler in a little bit, but I just want to go through really quick at how like a usual compiler looks like how the stereotypical compiler looks like. So here we have like a typical compiler lasagna. It typically looks something like this, but it can look very different as well. There can be more layers, there can even be less layers. We usually start out with the source code. This is a really simple like demonstration language. I just like invented, so it's not anything in particular, but it's really simple example. So we have a function that takes a single variable a, we multiply it by 2, and we multiply it by 2 again. So then we parse that into a syntax tree. So you can see here the argument on the left, and then the tree of expressions inside the body on the right. It's just a graphical display of an abstract syntax tree. Then that gets lowered into a IR, which stands for immediate representation. And the reason why we do this is that then the compiler can, the IR is usually at a different level of abstraction than, or each IR in a function is usually at a different layer of abstraction. So then the compiler can do different things and perform different transformations on each layer. So in this case, we see that the first expression on the bottom gets loaded into just a simple a times 2. And then the second one, just multiply that by 2 again, and then returns it. So then we have the optimization. So here you see really simple and easy optimization opportunity where we just, the compiler can see that we multiply a variable by two times. So that's the same as multiplying it by 4 and just returning it. And then finally, lowering to the target. So this is just like a simple example of like a bytecode or a assembly format where we just take a variable from or value from the stack, multiply it by 4, and we return that. So let's apply this to the Lumen compiler. So this is a high-level map of our compiler pipeline in Lumen. We can see on the top here that we have both a front end for regular Erlang, which should hopefully, we have really nice error messages, and compiling directly from Erlang to our internal representations hopefully makes it so that you could use our compiler for developing Erlang as well. And then we also have, for supporting the Elixir compiler and others, we have possibility for reading in abstract Erlang, which is something really easy to get from the Elixir compiler. We read those two into our internal Erlang ASD, which then gets lowered into what we call for EIR, which is a unified IR that we use internally in the compiler for Beam code. There are different dialects of EIR, and all our specific transforms and optimizations on Erlang code that's specific for like Erlang optimizations happen on this level. Some examples of this is pattern match compilation, where you take a full pattern match and you compile it into sort of a sequence of tests on values. A lot of optimizations go in here and more. We then, for Lumen, we go into MLIR, and which is an IR that's part of the LLVM project, upstreamed recently to LLVM from TensorFlow. And MLIR enables some really, really interesting optimizations like F-line optimizations, which do optimizations on memory accesses, which is used in like machine learning code to optimize it. So like that enables some really interesting things in the future, possibly. We then lower further into the LLVM IR, which can then be used to target like WebAssembly x86, 64, and many, many others. And just to note that a lot of languages use LLVM, like Rust, Swift, yeah, a lot of more as well. A lot of languages, C-lang, use LLVM for their targeting. So all of this, the entire thing, the entire pipeline is the Lumen compiler. You take the Lumen compiler, you run it on your project, and you get an executable for your target. But what's also interesting is that the upper layers here that are specific to Erlang and Beam languages, but they're not specific to Lumen at all. They're in a separate repo, they're a separate project that's called EIR. Lumen is our primary focus right now because Lumen is the only other project that uses EIR. But we're really open for both other backends. Like there is a Beam backend that's mostly functional for targeting Beam. So the Beam bytecode. And we also have another front end for core Erlang, and we're really open for front ends for other Beam languages directly, which would be really interesting. And they could then provide us more info, like if you have a statically typed Beam language, then that front end can provide us with more type information, which would enable our optimization passes to make better decisions and generate better code. Now, I actually talked about EIR before, back in May 2019, and that was before it was used in Lumen, but a lot has changed since then. So I'll go So I want to cover EIR a little bit, and not the project, but the IR there in the middle, because that's where a lot of the interesting beam-specific optimizations happens. And yeah, that's a cool part. So what is EIR? It's a quite novel IR design in the sense that it's based on a relatively new research paper called Thorin. It's sort of a hybrid between SSA and CPS, if anyone knows those two. If you don't worry about it. I'll go through some examples. So this is like how a really simple Elixir function would get lowered into EIR. You have my function there, takes a single argument, returns OK in that argument. If you look down at the EIR there, that's the EIR, the textual format at the bottom. You can see at the top, we have the function name and the arity. Then we have a block. This function has only one block since it's so simple, but a function can have arbitrarily many of them. There are a couple of arguments. And what you might notice that's a bit strange is that you see the normal arg, that's the third there, but there's also one called ret and one called throw. And these are what's called escape continuations. And what that means, I'll get to in a little bit, but this is an operation. So a block can only have one operation. And only one. It needs to have one, and it can only have one. This is a call operation. So that calls the value you got in as the first argument, ret, with a tuple that's created right above here. And that's created with a sort of, with a thing called a primop. So here it's, the tuple is created inside the block. But one really interesting thing as well is that a primop isn't really located inside any block in particular. It's sort of floating in the graph in the IR. And the only thing it's limiting where you can, when you create a primop, the only thing limiting where you can actually use it is which arguments, which values it references. So you can't use a primop somewhere where some of its arguments are out of scope. So some interesting properties we get from this is that you'll notice that like real values only can be created from arguments. And you can see that at the top there, there's 3 arguments created or values created in the argument list of the entry block. Primops, like the one creating our tuple, they're infallible. They can never fail. They're pure. They can not perform any side effects. So their location in the IR don't matter at all. Returning and throwing values are both represented as just a regular call, right? You're just calling a value to both return, and it's the same with throwing, except that you're calling the throw continuation. For another simple example, a bit more advanced, here you see that you have an Elixir function with 2 clauses, one that pattern matches on the value 0 and then returns bar, and another one that just fallback clause that returns pass. So looking at the EIR, you'll see the actual match being done here, where it's matching on the argument. If it's the value 0, then it's going to branch 1. And if it's anything else, then it's going to branch 2. And branch 1 and branch 2, those are names of blocks that you see below here. And you can see that if you branch to branch 1, then it calls the ret with the bar atom, and if branch 2, then it's calling a ret with pass. So that's in effect doing a return with one of those atom values. So you also notice that we're accessing the return continuation that's defined in the arguments of the entry in a different block. This is allowed since control flow can never reach. There's no way for the control flow in the function to reach any of those 2 blocks without going through the entry, right? The entry is the only entry point in the function, so it needs to go through there so we can use those values. This is how our scoping works in EIR, and it's always how our scoping works in EIR in all cases. Yeah, so for another example, this is where it starts to get a bit weird. You can see we're returning a closure we have a function bar that takes a single value A, returning a closure that takes B, and then returns a tuple of them both. And the EIR, you'll see that in the entry block, we're just calling return at once. We're not really doing anything, but we're calling it with another block as the argument. And then you'll see the other block below there, which here takes ret and throw as well, but like another variant of it. And it's a single argument B. And then it calls cret with the A and B arguments. So how does this actually work? Since this IR is based on Thorin, which is a hybrid between CPS and SSA, every single all control flow inside a function is based on calls to functions, and functions are first class in the IR. So you'll notice that in the early examples where we branch to other blocks, you can think of that as doing a capture of a block as a function, and then the operation that gets it just does a call to that function. So this is different than regular continuation passing style, if you're familiar with it. It's totally flat scope. There's no nesting of blocks. But there is an implicit nesting in the sense that you can imagine the close block being sort of implicitly nested inside the entry, since it's referencing values from it, right? So nesting is implicit, done by data dependencies in the code. But note that although all control flow in the IR can be thought of as function calls, this does not mean that all control flow becomes function calls. Like for control flow within a function, we just compile to regular control flow in WebAssembly or native. So why do we do this? One really nice advantage is that it's an extremely uniform representation of control flow in a function. Return, throw, branching, calls, everything is represented in the exact same way. Everything is represented through calls or captures of functions. So a call to those first two arguments in the blocks that I call for return continuation and escape continuation, those are control flow returning from a function. And calling blocks is control flow within a function. Calling a function is just like a regular function call. So everything's represented in the same way. But this means is that all control flow can be handled the same way when the compiler is working on the code. Optimization passes can handle everything identically. And this also means that almost all modifications to a function in EIR is done by a single primitive that's really flexible called lambda mangling, which is also described in the Thorin paper. So let's look at how a compiler pass does this in our IR in specific. So here we have a function called a bar that just calls another function directly with that single argument. And this is a really, really classic example of a tail call, since the beam guarantees tail calls are tail call optimized. We need to do that as well. So let's look at how the compiler would do that. This is how, so far in the other examples, I've shown really well-formed IR that's pretty minimal and easy to understand. But any front end that generates EIR would probably generate some like additional boilerplate, like useless function calls and that kind of stuff. So we need to clean that up with the different passes in the compiler. So we have the main part here. That's the meat of the function, right? That's we're capturing a function, mod foo, array1, and we're doing a call to that function where we branch to block 3 if we or B3 if it succeeds, and it branches to B2 if it does not succeed. And there's also like a totally useless branch here from the entry block to B1. We could totally just like plop that function call, the main function call in the function inside the entry without any semantic changes. But that's just the front end generating slightly worse code than it could. And we also have here our success and throw block handling the two. which just takes in for the throw path 3 arguments, and it calls the throw continuation with those 3. And for the return path, it just takes 1 argument, calls the return continuation with that one. Those are the continuations we get in as arguments in the entry. Let's look at what a compiler pass would do here. We'll look at the return path, B3. You can see that it just there is sort of a call from the when we return from the function call in B1, then we branch to B3 and get the single argument that's the result, and we just call directly the return continuation with that value. So what we could do here is we could just substitute B3 in the function call with the return continuation directly. So the compiler pass can see that we're doing this in a bad way, and it can see that we can do it better by optimizing it. So the compiler pass would probably do something like this, where it just plops that function call into the entry, and it just replaces the return and throw branches with the continuations directly. And the interesting part is that this is exactly how tail calls are represented in EIR. Tail calls are represented by calling a function and passing the return and throw continuations of the current function directly instead of a block. So by doing sort of the IR cleanup here, just like you would want to do to simplify the function a bit, just tail call optimization just falls out of it because it's all done in the same way. There's no separate instructions for doing returns with a tail call or like different types of calls. So some of the compiler passes we have the graph simplification pass. That's the one that would do what we just saw. It does control flow simplification, eliminates tail calls in the way we saw, propagates constants, does simple constant folding, and predicts or eliminate branches. So if you have a static branch that's like if you branch on true, just the atom, then you can just remove the branch, right, and eliminate some code. We also have a closure inlining pass. And we have a pattern match compilation pass. And as another example of how these things play together is that the pattern matching compilation pass, before pattern matches are compiled to like simple match instructions, guards are represented as lambdas or as closures, as just nested functions within the current function. After it gets compiled, then that lambda gets called inside the function directly. And you branch on the return value of that call to the guard lambda. Then the closure inlining pass sees that you're just calling a function that's defined directly inside the current function, and it just like drops it in. It just removes the additional call and makes it a regular control flow. And then the graph simplification pass can go through and it can see that, okay, if you have no guard, then it's just if true, and it can just remove that and simplify the control flow graph. Yeah. So that's about it for what I have. Hopefully everyone got something out of it, regardless of what level you're at the compiler stuff. We're really interested in community involvement. We are all, the whole core team, present in the #Lumen channel on the Elixir Slack channel. So come there and say hi to us. We have open stand-ups every single week. See the Slack channel for a link to the conference. And we have archives of all prior stand-ups on the YouTube channel, and a lot of more information on the getlumen.org domain. Yeah, thanks.
Excellent, thank you. Amazing talk. We got a lot of questions. Your friend Luke has answered many of them already, but I will ask one out here. Hans, can you share a memorable struggle you faced on the project and what you learned from it?
So, like from working on compilers, the most interesting things I've probably learned is that how many like relatively problems that look really complex can be really simplified if you try to think of them as a graph and look at which algorithms are available for graphs and apply those. So an example of that is like the graph simplification path that takes in just like a really messy IR, and it analyzes the graph and sees where it can make better choices. So I really, thinking as things as graphs, that's something that's helped me really, really much here, and at a lot of other projects as well. A lot of things can be done by thinking of things as graphs. I don't know if that answered the question specifically, but like that's the thing that came to mind for me.